All right, guys, this is going to be the second half of 6.1. And in the first part of 6.1, what we introduced was, or reintroduced, you've probably heard of it before, is slope. And remember, we explored that graph and talked about the different rates of change or slope at each point in the graph and what that meant for the context of the problem for the delivery truck example. And then what we looked at is our different definitions for slope. We look at it as rise over run, or y2 minus y1 over x2 minus x1, or the change in the dependent variable over the change in the independent. Now, all those are the same thing in different language. And then we found the slope while looking, or the rate of change when looking at a table. We talked about the rate of change between different points in that table and what that meant, and how the rate of change of the slope was consistent throughout the table. And then we eventually graphed the values in that table and reviewed the ideas of graphing. And now what we're going to do is we're going to pick up here with graphing and slope kind of tied together. So what I want you to do is in your notes, try and identify the slope from 4 minutes to 8 minutes in the graph. Identify the slope from 4 minutes to 8 minutes in the graph. Okay, hopefully you've paused the video and given it a shot at your own. Let's talk about this together. Well, what we observe here is a leaking tank. Okay, and what's going on with this tank? Well, we see consistently over the course of time how many gallons of, we don't know what the liquid is, probably water. How many gallons have left the tank? We are trying to find the rate of change or the slope from time 4 minutes to 8 minutes. Well, how do we think about this? Well, we could think about this in the traditional sense. We could identify our two coordinate points here at 4, 3, and 8, 6. And we could calculate our slope using y2 minus y1 over x2 minus x1. And we could, it doesn't matter which one you label which. Maybe we label this as 0.1 and this one as 0.2. And then we say, okay, my second, or my y value in my second point is 6. My y value in my first point is 3. My x value in my second point is 8, and my x value in my first point is 4. I can simplify this down, and I get 3 over 4. Okay, 3 over 4 being the slope. Now, how would we interpret that? Well, let's think about it. What is your vertical change? It's in gallons. It's the amount of water that's left. What is your horizontal change? That is in minutes. So we're saying out of every 4 minutes, 3 gallons of water are leaving the tank. Now, why can I say every? Well, because this is a straight line, right? For sure, this is occurring 3 gallons left in the 4 minutes between minute 4 and minute 8. But because they lie on a straight line, we can say that is consistent, that 3 gallons are leaving every 4 minutes for the entirety of the graph of the leaky tank. Now, we could also simplify this down because we know 3 divided by 4 is 0.75. And what this would mean is that 0.75 gallons are leaving every minute. How do we put 1 minute? Well, if we divide this and we get 0.75, we can put any number over 1 in a fraction, and it will stay the same. So again, what we're looking at is 0.75 gallons are leaving every 1 minute. And you might have said, Mr. Carter, there's an easier way to think about this. And I would agree. Well, this is one way of explaining slope. We can also think about slope as rise over run. And you might have done it this way to find the slope. You might have started at the 0.43 and said, well, how do I get to the second point? Well, I go up 1, 2, 3, over 1, 2, 3, 4. So my rise, so to speak, was 3, and my run was 4. And again, this exemplifies the fact that no matter our method of calculating the slope, we're going to end up with the same thing. Okay, we went up 3 over 4. Either way, we're interpreting the problem. We're saying 3 gallons of water are leaving the tank every 4 minutes, which is the same as saying 0.75 gallons are leaving every 1 minute. Let's try another example. Let's look at the slope from 0 to 30 minutes. Again, pause the video, see if you can figure this out, especially after seeing the last example. So maybe you looked at the last example that I went through and you said, wow, when it comes to graphing, rise over run's a lot easier. Let's use that here. I like that idea. So we're going to find the slope. We're going to use rise over run to find the slope. Again, remember, m is our mathematical variable for slope. Well, what is our rise? AKA, how much do we change vertically? AKA, how much does our dependent variable change? Well, in this case, we are going up, so it seems counterintuitive. It's not really a rise, but we go down by 3. Okay, we go down by 3. Our rise is 3. And we notice we go over by 3 to get to our other dot. But be very careful. Be very careful. The temptation here is to write your answer as 3 over 3. But that's not correct. What did we forget? Well, here, since we're not going up when we're going down, the rise is not 3, but it is -3. Broadly speaking, anytime you move on a graph, if you go down and or left, you are moving in a negative manner. Okay, so we move down here, so we resemble that, or we write that as -3. Now we go over right, so the issue is not that we didn't put a negative in the denominator, because we moved to the right 3, which is a positive, just like moving up. But the issue is we went over 3 grid spaces, but that's not our unit. If you look at time on the x-axis, time is progressing by tens. So we did not go over 3, but we went over 10, 20, 30. Resembled by the 30 minutes. Be very careful with rise over run. While the easiest method to use while graphing, debatably, you must watch out for a changing scale. You must watch out for a changing scale. Okay? So our slope in this case would be -3 over 30, which could be simplified down to -1 over 10, which could be simplified down to 0.1. But again, you're probably noticing, just like in the last column, it's a little, or the last problem, it's a little easier to leave your answer as a fraction when we're talking about slope. Okay? It's a little easier to say I would go down 1 over 10 than it is to say I go down 0.1 over 1. Okay? Now let's do a little bit of interpreting in the context of the problem. What does our answer mean? Well, let's look. Our dependent variable is the height in inches of our candle. And our x variable is, or our independent variable, is time in minutes. So how can we interpret this? Well, the candle's burning, and so the wax is melting. So maybe this is a graph resembling the height of the candle. And what we're observing here is that the candle is going down 3 inches every 30 minutes, or in a simpler form, 1 inch every 10 minutes. Okay? And we can see here, if we want to do a little bit of more interpreting, the candle burns out at 100 minutes, which, as far as candles go, probably don't want to buy this one. Doesn't even last 2 hours. Either way, though, you can see how we calculate slope in graphs. Next problem. Using your knowledge of finding slopes given graphs, find the slope of a line given these points. Go ahead and try this on your own. Well, what we are observing here, hopefully you've tried it on your own. Pause the video if you're not done yet. What we're observing here is we, again, are being asked to find the slope, but we aren't given a graph here. We're not given a table or a chart or any visual. We're just given 2 coordinate points. Now, while rise over run is great for working with graphs, rise over run isn't really going to make sense here. Because when we make graphs by hand, a human error can come into play. If you don't draw your lines perfectly straight on graph paper, well, going up 7 might actually, you may mess it up and think you're going up 8. It's very easy to make mistakes with rise over run with hand-drawn graphs. So I think the more foolproof method would be to use y2 minus y1 over x2 minus x1 to find the slope. Again, if you struggle to remember, oh, Mr. Carter, does the change in y go on top or the change in x? Well, think back to the methods we are really solid with. Rise over run. What variable represents rise? Well, your y does. Well, rise is on top, therefore your y's should be on top. Similarly, your run, your horizontal movement, is resembled by the x variable. Is the x on top or bottom? Well, it's on bottom, just like run is on bottom. Okay? Again, when you're solving this, it does not matter whether you label your point, which point you label as the first point or the second point. I will label the left one as the first point, just because I read left to right, as most of you do here in America. And so I'm going to label the left coordinate point as my first point and the right one as my second. If you did it backwards, that is completely okay. Your numbers are just going to be flipped, but you ultimately should get the same answer. So what is my y2 value? Well, my y2 value in this case is 7. My y1 is 1. My x2 is 5. And my x1 is negative 2. Now notice, no matter what, I put subtraction signs in the middle. Those subtraction signs are part of finding the slope. That's how we find the change in the variables. Just because I have a negative number here for my x1 does not mean the subtraction sign goes away. It's not going to be 5 minus 2. It is 5 minus negative 2. So be very careful there. Always keep your subtraction signs, even if they are negatives. 7 minus 1 is 6. We know that 2 negatives make a positive. So 5 minus negative 2 is actually 5 plus 2, which comes out to 7. Therefore, our slope in between these 2 points is 6 over 7. 6 over 7. Okay, our final problem. We want to find the slope of a line given the following points. Then we're going to graph the points and their respective lines. So you have 2 jobs here. Number 1, for each set of points, find the slope. Then graph each set of points, connect them with a line, and see if your slope lines up with the picture you've drawn. So go ahead and try that on your own. Okay, hopefully you figured it out. Hopefully those instructions are clear. I hope they weren't too confusing. So what we're going to do is we're going to find the slope for each set of points to start out. In general, finding slope with a set of points, the best way to go, y2 minus y1 over x2 minus x1. So let's do that for each one. Broadly speaking, I will leave my left points as the first set of points and my right coordinate points as my second. So this will be 7 minus 5 over 4 minus 2, which equals 2 over 2, which we could simplify to be 1. My second set will be 2 minus 2 over 4 minus 1 equals 0 over 3, which can simplify to 0. My last set of points, we have 2 minus negative 1 over 4 minus 4, which gives me 3 over 0, which is undefined. Because we cannot divide by 0. Remember, 0 divided by anything is 0, but you cannot divide something by 0. 0 can never be the denominator in a fraction. That is undefined. And again, do not get tripped up if we look at the one in blue. Again, 2 minus negative 1 minus a negative produces a positive, which gives us the 3/0. So let's have a look as to what these look like graphically. Now that we found the slope for each one, now we start out by making a scale. I think it makes the most sense to go up and over by ones. Again, that will change depending on the context of your problem, but in this case, that's what I would recommend. And now what I'm going to do is I'm going to plot my set of points. Now be careful, you are not plotting your slopes. I want to make that clarification. You never plot slopes as points. Slopes are not points. Rather, they describe the rate of the change of the line that connects two points. Okay? So the point is not going to somehow be 2, 2 if we look at the one in green. Rather, we're going to plot the points 2, 5 and 4, 7. We're going to connect them with a line. And what we notice is that the slope is indeed up 2 over 2. Or we could even make it a little simpler. We go up 1 over 1, up 1 over 1. Okay, if you want to think about it as the slope of 1, and again, anything can be put into a fraction over 1, so it'd be 1 over 1. Okay, the slope describes the line between 2, 5 and 4, 7. It's not as if we plot 2, 2 as a point. So let's look at the other ones as well. Let's plot 1, 2. Oh my. Sorry about that, folks. These are not supposed to be negative numbers. These are supposed to be positive. Error on my part. So we're going to plot a point at 1, 2 and 4, 2. And again, we got a slope of 0 with this point. Oh, that second one needs a little bit of work here. And again, what we notice here is we got a slope of 0. But if we step back before the simplification, we had 0 over 3. And again, that would make sense. Right here, that says we go up 0 over 1, 2, 3, which indeed is what's illustrated by our graph. What's interesting about this, though, is that we notice a relationship where the slope of 0, our graph, with a slope of 0, our graph is a horizontal line. And if you do some further investigation, if you try looking at other points that are connected by a horizontal line, you will indeed find that in any case where a horizontal line is present in the graph, there will be a slope of 0. Okay? A slope of 0 means the graph is a horizontal line. Let's plot our final point, 4, -1. And 4, 2. And this graph, which had an undefined slope, produces a vertical line. A vertical line. Why? Because again, if you go back before we simplified to undefined, we were saying go up 3 and over 0. Okay, but that resulted in division by 0, which again produces undefined. Okay, so any graph with an undefined slope, or if you run into a slope that is something divided by 0, it will not be a function, okay? And it will produce, an undefined slope produces a vertical line. Guys, that's the end of section 6.1. As always, email me with questions, and good luck on the practice.